and Informatics at the University of Sussex. And he will tell us about information, causation, and emergence in neuroscience from a personal perspective.
Hi, everyone. First of all, thanks very much to the Fields Institute and John Griffiths in particular for inviting me here to speak here. There's a slight apology that the title of my talk is not quite the same as it might have appeared on the programme, which mentioned emergence and dynamical independence, which I shall be speaking about today as well. But my talk today is going to be, pretty much what it says. It's a bit of a kind of a ramble through my kind of path of discovery in computational neuroscience and consciousness science and emergence. I've called it a personal perspective, which is not supposed to be a get-out clause if I speak complete nonsense. So if I do speak complete nonsense, I encourage you to take me to task for it, and I welcome all kinds of questions. So first of all, just a brief kind of roadmap of how I got to this stage, if you like. So I'm originally a pure mathematician. I started off studying differential geometry, Riemannian manifolds, and Lie groups. That was at Cambridge. Then I spent 15 years or so as a software engineer in telecoms, and sometimes also as a musician. And you can figure out which paid better and which was more fun. Then I became quite enthused by the artificial life movement in the late 80s, early 90s, very influenced by the work that was going on in Santa Fe and elsewhere, including one Stuart Kaufman and his splendid book. So I got this interest in evolution, in artificial neural networks, complex systems, cybernetics, robotics, inactivism, information theory, and in fact, especially evolution, natural and artificial. So I returned to academia in the mid-90s. In particular, I went to Sussex University to do the evolutionary and adaptive systems course there, which at the time was a kind of, I suppose, a European centre for all things artificial life, but with quite a specific kind of feel to their attitude, their perspectives on artificial life. So I ended up doing my PhD there for the Centre for Computational Neuroscience and Robotics, which sort of semi still exists, although it seems to be semi-notional at the moment. My actual PhD was in the neutral theory of evolution under Inman Harvey, who's a mathematician turned philosopher. Sorry, mathematician turned philosopher? I suppose so. He was both, which is actually fairly unusual. One of the highlights of my time there is that I got to meet the late, great John Maynard Smith, who was one of the leading figures in 20th century evolutionary biology. And in particular, he was on my PhD committee, so I would meet up with him a couple of times a year to discuss the progress, which was a great privilege at the time. And he was very influential as it turned out in the course of my studies. So one particular anecdote is that for my first PhD meeting, so we met in the Swan Pub, which is just on the edge of the university in the village where Maynard Smith actually lived, and where he used to kind of hold supervisions and do a lot of his work, in fact. So at the time, I was in fact intending to do my PhD on an information theoretic account of evolution theory. And I'd prepared as a kind of, I'd worked out one information theoretic account of something very specific in evolution theory called the error threshold or error catastrophe, a well-known kind of evolutionary genetics phenomenon. And so I presented this to Maynard Smith, and what he said would turn out to have quite an impact on my further academic career, which is that he said, well, that's very interesting, but what do we know now from that we didn't already know? He was, I think, quite gently, because he was a kind man, telling me that the work I had done was those words you never want to hear, it was not even wrong. Now, well, the upshot of it is I heeded his advice a bit begrudgingly. He did say at the time that he then gave me an account of how he and his mentor, back in the 40s, his mentor being, what's the name of the, they will come back to me in a sec. How back in the 50s, they decided they were going to work out the evolutionary account of evolution theory. And they thought it would take them maybe 6 months or so. And he said, look, 50 years later, nobody's done it. So I don't know how to take that at the time. I thought, well, just because you couldn't do it, you know. On the other hand, I thought basically that was good advice. So I did my thesis on a topic called the neutral theory of evolution. So there you go. Then I spent a couple of years as a mathematical researcher for a hedge fund, because I wasn't sure what to do next, and it was a nice offer. It was kind of early days of algorithmic trading. I think it was one of the first companies in the UK, at least, to go completely kind of human-free trading. And it turned out to be very useful. In particular, I learned an awful lot of time series analysis, amongst other things. Then I did a postdoc in network theory, in spatially embedded networks, and learned a lot of network theory. At which point I hooked up again with Anil Seth, who had just founded the Center for Consciousness Science. Now, I actually knew Anil back from the master's course days in the mid-90s. And Anil had gone off to study with Gerald Edelman in San Diego and got very excited about consciousness science and so on. Also about things like Granger causality. Anil was one of the first people to actually use Granger causality in a neuroscience scenario. And Anil basically said, right, yeah, you're a mathematician, you know time series analysis, you know network theory, you should come and work with me in the Consciousness Science Center. My first response was, well, one thing I don't know anything about is neuroscience. So I still don't know anything about neuroscience. So what I did find was that mathematicians and neuroscientists have a kind of a mutual imposter syndrome going. So anyway, it kind of works out. So what I'm going to talk about today, what I'm starting off talking about is kind of leading up to how information theory appears. What is its status? What's its role in neuroscience? So first of all, in science generally, so traditionally science is all about mechanism, and in particular causal mechanism. So there's what's my pointer? Here we go. So an equation like that's a differential equation, and what it's telling you is how some variable out of a system of variables changes in response to the state of all the other variables with time. And it's probably a parametric model, so there seems to be some parameters in there. So we have a parameterized causal model, because science is all about models, isn't it? So fine, and that's fine. That takes us a great distance, except when we don't know everything. So we're looking at some situation. Perhaps we don't have access to all the values of all the relevant system variables, all the variables which are going to affect the system. Our measurements are probably inaccurate, or we don't know or can't find out the values of all model parameters. In other words, always, because that's always the case. One of those things, probably all of them, is always the case. In other words, there's always uncertainty, and information theory is the right kind of maths for quantifying uncertainty. So very natural that we should be looking at information theory. So now, of course, you have models which explicitly incorporate uncertainty. So there we have a first-order autoregressive model. The system variables now are written in capitals because they're random variables. And that system process, x of t, is a stochastic process. So what about the epsilon of t? So that innovations process, as it's sometimes called, depending which domain you're in, encapsulates the uncertainty. It represents the uncertainty. So it is essentially, it represents everything which is not explained by the model. So that could mean real noise. And I've said whatever that means outside of a quantum context, because what constitutes noise for you might not be noise for somebody else. But so I'm not speaking about anything quantum here. So anyway, but in many physical scenarios, it's the best interpretation of that process noise is a failure to include some latent or some unmeasured influences on the system. So stuff which is not explained by the model because surely for very good reasons you didn't or couldn't include it in the model. So the mechanistic aspect of that model, you might say, is going to lie within those autoregressive coefficients. So that Aij tells you, modulo some uncertainty, how variable xi changes according to the current state of some other variable, xj, and that a change in xj is reflected. That one is reflected. So a change in xj is reflected at the next time step in x of I. So you might say, looking at that interpretation of that equation, that those structural coefficients, those Aij, should constitute a natural quantitative measure of the causal effect of variable xj on xi, right? Because xj influences what happens next to xi at the next time step. But that doesn't seem to take into account the uncertainty represented by those innovations. You know, you think, well, shouldn't that be in the picture as well? And another question is, what if you transform the variables? Sorry, I'm getting some, I think you're getting some interference here. Is that me? Oh, my phone. I don't know why. Sorry, it must have filed something. Anyway, sorry, to get on there. Yeah, so another problem with that is what happens if you, say, transform the variables instead of x of I take log of x of I, for instance. What happens to that equation? Well, it all kind of gets a bit muddled, and those particular coefficients become maybe some other coefficients in some different looking model. Everything gets a bit messed up. So what are we going to do about that? So maybe those Aij, those structural coefficients, those mechanistic coefficients of that model are not actually a good reflection of the causal effect within that model. So now, there is arguably a more principled information theoretic quantification of the causal effect of variable xj and variable xi, which does take the uncertainty into account and doesn't care about the units or the scaling of variables or anything. And that is this conditional transfer entropy term here. So that says the transfer entropy from xj to xi conditioned in all the other variables in the system. That square brackets xij denotes all variables except for xi and xj. So transfer entropy doesn't even care about the model which generates the process. All it cares about is the statistical structure of the process itself, if you like. It's non-parametric, and it's defined purely in terms of Shannon mutual information. So what it says is that the transfer entropy from y to x conditional on z is essentially this. What does y, the source variable, if you like, at a previous time tell you about the current value of x, given what the past of x itself already tells you about the current value of x, and what the past of the conditioning variable tells you. Just a note on the notation, this tau represents lags, it represents history. It could be one lag, it could be an infinite number of lags. It's just a convenient notation. So some people are going to say, but wait, that's not causality, that's Wiener-Granger causality, and always in quotes because, well, I'm going to leave the word on that to Clive Granger himself. So this is what Clive Granger had to say, and that was in his Nobel Prize lecturer in 2003. So first of all, he describes Wiener-Granger causality as follows. And he says, a paper by Norbert Wiener contains a statement about causality that has just two components. Well, it's not actually two components. But anyway, first of all, the cause occurs before the effect. I doubt there are going to be many who will argue that one. Secondly, the cause contains information about the effect that is unique and is in no other variable. And we'll come back to that. Then, in somewhat cynical mode, he had the following to say. He said, at the time, I had little idea that so many people had very fixed ideas about causation, but they did agree that my definition was not true causation in their eyes. It was only Granger causation. I would ask for a definition of true causation, but no one would reply. However, my definition was pragmatic, and any applied researcher with two or more time theories could apply it, so I got plenty of citations. Of course, many ridiculous papers appeared, and still do, I might say. But anyway, so okay, that's what Granger himself had to say about this. And of course, a lot of people now would say, but true causation was worked out by Judea-Pearl. Pearlian causation, it's based on interventions or counterfactuals, if you like. So interventions you make in the system, you plot it there, and that has an effect there, and you can see that effect. So that as pragmatic scientists, and as Granger says, his definition is pragmatic, we do need to take on board this, which is that never in the history of the universe has a counterfactual ever happened. That's kind of the definition of a counterfactual. And okay, that's a bit cheeky, and people have assured me that, in fact, you can be quite pragmatic about Pearlian causation. But anyway, I feel uncomfortable sometimes about taking into account stuff which didn't happen, maybe because it couldn't have happened, or whatever. So, as I say, I'm kind of sanguine about this, and philosophers have been debating the idea of causation for centuries, millennia possibly, and so I'm okay with Wiener-Granger causality, or in its transfer entropy guise, or in Pearlian causality, either of which being a rather than the notion of causation. So that's fine. So some folks may be happier describing it into just leaving the causal word out of that and calling it transfer entropy, information transfer. That's the clues in that name. Some vexatious people will cavil about that too, and they may have a point. So I'm going to have a look at that a bit. So they may have a point, not necessarily a resolution. So firstly, there's Granger's point 2, and I'll say that there's actually 2 points there. So the cause contains information about the effect that is unique, and the cause contains information about the effect that is in no other variable. I'm going to take the second one first. So this seems to imply that in principle, if you're going to use Wiener-Granger causality, you have to condition on the effect of every other variable in the universe that could potentially influence your system. So that would have been those xij in my previous equation. All system variables except for xi and j. This is hard. You don't know what they are. It's very hard indeed. The next point is, what does unique mean in that context? What does unique information mean here? We all understand Shannon information, but Shannon doesn't say anything about unique information. So how do we characterize and identify unique information? So now there's one recent branch of information theory which claims to have an answer to that question, and that is the partial information decomposition, as it's known. I don't know how many people here might be familiar with partial information decomposition. A few, not everyone. So the idea of partial information decomposition is to decompose Shannon mutual information between, say you've got 3 variables, A, B, and C. You want to know what B and C tell you about A. So in the simplest form, partial information decomposition would try and decompose what B and C tell you about A into information which is unique to B or unique to C, which is redundant because it's in both B and C, or is synergistic. It only arises through a combination of B and C. And that's a tremendous idea. This first appeared, I think, in a paper by Williams and Beer in around 2008, maybe earlier. Very lovely idea. There's a problem. And I'm going to do a little rant here because this is something which comes up a lot in my area of work. So as it stands, PID, partial information decomposition, is not a thing. It is in fact around 40 and counting different things. And that's because no one can agree on how PID ought to behave. And there have been various attempts at axiomatization. Nobody can agree on that. And some of the proposed axioms, all of which seem really reasonable when you read them, turn out to conflict with each other. It's turned out to be a much thornier problem than people first suspected. So I don't have a problem with the idea of PID or even its use. But if you're going to use PID in your study, you need to tell me, you need to tell everyone which PID are you using, because there are 40 plus, and why are you using that one? Because they're all very different, and some of them very counterintuitive. And if you're going to tell me a footnote, please tell me right up front and not in footnote on page 17 of the supplementary material. And I say that seriously. I've reviewed papers which said we used PID. First of all, I'm thinking, no, you didn't. You used a PID. And then I'm waiting for them to tell me which one they used and why. And they don't. That's not right. Anyway, rant over. And that's a shame, because what you'd really like to be able to say after Clive Granger is that transfer entropy is that same expression as before, but now you're looking at the unique information between the past of X and past of Y, which affects the future of X. That would be closer to I think, what Granger himself actually meant. And that would be neat if only we could agree on what that UI, that unique information, actually means. So just to say that given that you've got a PID, the whole theory behind it is actually rather elegant. It's really rather beautiful. If you want to read about it, there's this paper a few years ago by Aaron Bietknecht, who's a young German researcher I've worked with before. Very beautiful paper, everything you want to know about the structure of PID. So to push on, so we've talked about Granger causality and also transfer entropy. What's that about? What is the distinction there? Well, you could say the distinction is in this paper by myself from 2009. Now, I'm slightly uneasy with my own paper, which says what it says in the box. Granger causality and transfer entropy are entirely equivalent for Gaussian processes, for Gaussian variables. I'm uneasy about this paper because when I published it, it was something I thought everybody basically knew. And somebody came up to me after a symposium and someone said, oh, that was interesting, you ought to publish that. And I said, well, I thought everybody knew that. And they said, well, I don't know if they do, but I've not seen it in the literature. So I wrote the paper, which was one of the easiest papers I've ever written. It's not terribly deep results. I sent it off to physical review letters, and one of the reviewers said, well, I thought everyone knew that, but I can't find it in the literature, so there you go. And this gets way more citations than I'll ever get for any other paper, because if you Google Granger causality and transfer entropy, this is what comes up. The importance of naming a paper well. But no, this is not the paper we want. It's this one. This is the paper which establishes what I think is the kind of true relationship between transfer entropy and Granger causality. What it says in a way is that Granger causality is a kind of parametric cousin of transfer entropy. In my head, they're kind of the same thing in the following sense. So the summary is that in a parametric scenario, for pretty much any class of Markovian stochastic process models, for which you might read predictive models, Granger causality generalizes naturally as a log likelihood ratio statistic under the null hypothesis of vanishing transfer entropy. And in the large sample limit, that log likelihood ratio sample statistic is asymptotically equivalent to the transfer entropy itself. So this actually generalizes and subsumes this earlier result, but it's much more general, it's much more powerful and less trivial. So for me, this sort of encapsulates what is the relationship. Granger causality is a parametric form of transfer entropy. Okay, So, and for people, I've added this because often when you say Granger causality, people say, oh, yes, but that's all about linear Gaussian systems, isn't it? This paper contains no linear or Gaussian assumptions. You don't need Gaussianity, you don't need, these could be non-linear parametric models. It all works. So now, so that's a very satisfying result on a theoretical level, and it's useful for some scenarios. For instance, transfer entropy estimators for discrete valued Markov chains. You can actually use that result directly. It gives you sample distributions for the transfer entropy. More generally, the problem here is that for nonlinear models, even Markovian models, you need, this is likelihood theory, you need the likelihood function. That's often very hard, if not intractable, to work out. But a few years ago, this paper came to my attention. The title is Granger Causality Maps of Diffusion Processes. And that was by a young German PhD student called Benjamin Wahl, who's at Oldenburg University. This kind of landed in my lap because, well, I'll come to that in a minute. So the summary of this paper is that for an important class of nonlinear stochastic processes, and specifically Langevin systems, physicists will be very familiar with these. They are essentially stochastic differential equations, if you like, also known as diffusion processes. And they're ubiquitous in physics, in econometrics, in biophysics and beyond. So what Benjamin Wahl said, he did what physicists do, which is when you're faced with kind of intractable nonlinearity, you linearize locally. And in this case, what Wahl did was to linearize locally in the phase space of the system. And so you get a local process, a locally linearized process at each point in the phase space of these Langevin systems. And then you can work out the Granger causality at each point in the phase space. So he called it a map. So you have a map given a pair of subprocesses, the Granger causality for one process to the other, you can compute at every point in the phase space. So you get a map from the phase space to Granger causalities between these sub-processes. And furthermore, you can actually average, you can integrate that map over the stationary distribution or over the entire phase space possibly, to get a global Granger causality statistic. But there was a problem, and this is why Benjamin Wahl had contacted me. I mean, I thought the paper was fantastic. I thought it was one of those things where you thought, gosh, I wish I'd thought of that. Anyway, I didn't. Benjamin did. There was a big problem. So the locally linearized dynamics are what's known as vector Ornstein-Uhlenbeck processes. So they continuous time autoregressive processes. They're kind of Brownian motions, if you like. They turn up in all kinds of places, including in econometrics and so on. And Benjamin Wahl was calculating the Granger causalities by by discretizing these and simulating them and so on and so on. There was a problem, which is that in some regions in the phase space, these local linear vector Ornstein-Uhlenbeck dynamics would be unstable. They would blow up. They were explosive processes, which meant that you couldn't calculate, at least not the way Benjamin was doing it, you couldn't calculate the Granger causality for them, which meant that Benjamin Wahl's maps had big holes in them, sometimes very big. I'll come back to that in a minute. So this is very new work. It's not, I was going to try and get this up onto archive at least before coming out here. I didn't quite manage it. So in this year, we managed to actually solve that problem. So what this says is that essentially we can fill in the holes, that we may calculate the Granger causality for vector Ornstein-Uhlenbeck processes, which is equivalent to the transfer entropy for those processes, even in the unstable case. And in fact, not only that, but you can calculate them analytically from the parameters of the Ornstein-Uhlenbeck process itself. And for Langevin systems, locally, these parameters are the Jacobian matrix of the drift function, for people who know about Langevin systems, and the variance-covariance matrix of the diffusion which is the fluctuations in the system. So essentially, yes, you could fill in the holes. And just to get some flavor of what that result looks like, it turns out that you need to solve a bunch of what's known as continuous time algebraic Riccati equations. Now, if you know anything about control theory, you might have come across these. Why they should turn up in this context is an interesting story, which I don't have time to go into. But anyway, you get a nice answer out of that. It's something you can calculate very easily and quite computationally cheaply. And there's another peculiar thing about this, which is that this quantity, this Granger causality rate, turns out to be invariant under the overall intensity of the noise. So if you scale that variance-covariance noise matrix by some factor, that Granger causality rate does not change. So I thought, well, okay, what happens if you just crank it all the way down to 0? You still get an answer. You still have a perfectly well-defined Granger causality rate. But the system you have now is essentially deterministic. You have a set of ordinary differential equations. Now, of course, a lot of physics, a lot of everything is ordinary differential equations. So you can do transfer entropy for deterministic systems. It sounds a bit weird. So, as I say here, sorry, I should have put that up earlier. So you can calculate these Granger causality maps for these classical dynamical systems. The noise doesn't disappear, so you're left with this kind of ghost of noise represented by the, if you like, this variance-covariance matrix, which has been scaled according to something. And I like to think that you can interpret that as some kind of infinitesimal fluctuations, if you like. I mean, this is information theory. You need stochasticity. So the stochasticity doesn't really go away. It just gets very, very, very small. So, and I'm going to illustrate this just to show you that this really can be done very easily. Just to mention, so I'm going to demonstrate this for the Lorentz system, which is the classical chaotic system. Just as an interpretation of, just as a demonstration that this can be done quite easily. So this is just to mention. So in chaotic systems, especially, it is not at all surprising that they will be locally unstable somewhere. In fact, I think there's probably some theorem which says that while you may have global stability, you probably need local stability. So here's what you get. So this is the maps of Granger causality. So the right-hand pictures are the Granger causality maps between all so there's 6 of these, bidirectional between the different variables in the system. On the left here, we have a map of stability. So the thing to notice about, let me go back again. The thing to notice about this is that locally, you're only stable when those eigenvalues of the Jacobian matrix are negative. It's only the red bits, all the gray and red bits are unstable. So as you can see, a lot of that attractor is actually unstable. So this, you couldn't have, Benjamin Wahl would not have been, these maps would have been mostly holes. I actually worked out that if anyone's come across the Restler system, chaotic system, it turns out to be unstable everywhere while being globally stable. It's like one big hole. So anyway, I'm going to now change the topic a bit. How am I doing for time, by the way?
You're good for
okay, I'm going to have to speed up. Sorry about that. Okay. Yeah, we'll see how we go. So I'm going to change the topic a bit, which is, well, actually jump back a bit now, which is, again, I'm going to talk about information theory in neuroscience. And this paper, which appeared, I think it was 2017, got quite a lot of attention. And it's called A Study of Problems Encountered in Granger Causality Analysis from a Neuroscience Perspective. It appeared in PNAS. Now, this paper turned out to be, it's seriously flawed in some ways. First of all, half the paper is devoted to problems which turned out had actually been solved many years previously by both myself and other people. And the authors were very graciously conceded that that was the case. I think it also misunderstands the use of range causality in statistical inference, but nonetheless, I've actually cited this paper quite frequently because I think it articulates very nicely a very real debate. So what Stokes and Purdon, what their contention is essentially that in neurosciences are interested in mechanism, not causation in the Wien-Lagrange sense or information theory. They say of primary interest is mechanism. And the way they put it very, very clearly is, so fundamentally a mechanistic understanding of the neurophysiological system is sought, and as a result, the structure and functional interpretation of the models are most important. In particular, neuroscience investigations seek to determine the mechanisms that produce effects observed at a particular site within a neural system or circuit as a function of inputs or causes observed at other locations. Now, I've already said, I think there are some problems with that perspective, but I think it's a debate which continues and is worth having. And I'd say they express that very clearly. However, they don't really offer any clues as to how you might fix this, because especially, as I say, you have problems with, how do those structural coefficients reflect the noise? Well, they don't. And what happens when you start changing variables? Those quantities are not transformation invariant. You may get different answers if you measure spectral power in power or in log power in decibels. Nobody wants that. This paper listed a bunch of responses, including a couple from myself and colleagues, including, I should say, one rejoinder to PNAS, which was eventually published after they completely blanked us in our first request to publish a rejoinder, until we actually wrote to Stokes and Purdon and said, hey, look, this is our criticisms. We're getting no joy from PNAS. What do you think? And they were great about it. They actually basically went back to PNS and said, yes, we'd like these people to publish their response, which I thought was fabulous behavior for, which you don't always get in science. So full respect to Stokes and Purdon, and I think that debate still goes on. So now I'm going to eventually get round to emergence. So this is actually from a talk I gave a few months ago about the kind of the status of emergence theory of late, and in particular in neuroscience. So what I'm saying here is, I'll read down. In recent years, the impetus in research into emergence, broadly characterized as the relationship between microscopic and macroscopic levels of description of a complex system, has arguably shifted from the ontological, if you like, philosophical, what is the nature of emergence, to the epistemic, the more practical, how shall we quantify emergence? And that's a pattern in science. Science tends to go from talking about what things are to how things work. And I think that's happened in emergence theory in the last few years. So in particular, several information theoretic approaches to measuring emergence have appeared in the past few years. In these studies, two apparently unrelated key principles have come to the fore. So there's mereology. So mereology is used in philosophy to mean the study of part-whole relationships. So mereology, with a focus on causal relationships between the whole and constituent parts of a system, and the idea of informational closure, which in the context of emergence is concerned with autonomy of the macroscopic with respect to the microscopic dynamics. I think it might have been Bertschinger, I should have cited this, was the first to use the term informational closure in that context. And so measures of emergence based on these two distinct principles are exemplified by causal emergence and dynamical independence, respectively. Causal emergence being, by Fernando Rosas, Pedro Mediano, and others, and dynamical independence, myself and Daniel Seth. So these are the two papers. Now, interesting thing to note is that at the time we were researching for these papers, both Fernando Rosas and myself were, for the most time, working in the same building In fact, he had an office across the corridor from mine. And we used to talk to each other about all kinds of things, including information theory. Yet somehow we'd never discussed this, and we didn't know the other lot were working on it. And so we both, within a couple of years, came out with these two, as it turns out, very different theories of emergence. So first of all, I'm going to whiz through these, just a bit of technical stuff, just the kind of context of emergence theory. So we want a complex dynamical process representing the microscopic level of description of the system at hand. Stochastic processes, typically it'll be an ensemble of interacting individuated elements. Don't worry too much about the maths here. And the time evolution of the microscopic dynamics is frequently defined as a kind of dynamical law of some sort. So it's a time distribution over time of these dynamical variables. And the other thing you're going to be talking about is a macroscopic variable for a given microscopic system. The essence of that is that a macroscopic process will generally, certainly in information theoretic terms, satisfy some kind of supervenience criterion. Again, that comes from philosophical literature. What it really says in practice is that a macroscopic variable doesn't bring anything new to the table that's not already there in the microscopic system. It's essentially, it's kind of saying there's no magic. It doesn't bring anything new to the table. The kind of canonical example of that is simple coarse graining. So you have a map from the microscopic to the macroscopic phase space, which will generally be of a low dimensional cardinality, so it affects dimensional reduction. So that's what we talk about. That's what we say when we talk about microscopic or macroscopic variables. So they look at information dynamics. It's very much in a predictive sense. Both of these theories we're going to look at. They consider how various processes, parts of the various systems, predict other parts of the system. So brief word, when you're doing prediction based on history. This is just shameless plug for our book. But making a good point is that using sufficient history can be very important. And in this book, which is by myself and co-authors Terry Bossemeyer and others, we make the point that if you don't use enough history, you can get spurious results when calculating transfer entropy. We demonstrate that very clearly with a toy example, which is not good news for transfer entropy in particular, because transfer entropy needs a lot of data. Introducing more lags, you get these combinatorial explosions. Anyway, the best thing about this book is that when people say, "Oh, you know about transfer entropy," I can stand there and say, "Yeah, I wrote the book." You know, so it's always nice. Anyway, so what people think of when they think about emergence tends to differ a bit depending on which scientific domain they're from. So take this with a pinch of salt, but I'm trying to get a broad perspective here. So philosophically, philosophers tend to think about emergence in terms of mereology, in terms of parts and wholes. So, they talk about the sums being greater than parts, about whether there is or isn't downward causation, so on and so on. Physicists, on the other hand, tend to, as we'll see, be talking more about the idea of informational closure. So physicists do lots of coarse graining, and then they look at things like, is the Markov property, for instance, preserved under coarse graining? And that, whether it is or not, turns out to be a question of informational closure. In biology and in neuroscience, maybe both. So, for instance, biological structures individuation is very much, I think, a mereological question. Ideas of things like autonomy, of homeostasis, of autopoiesis, again, are more on the information closure side. Things like flocking and swarming systems, I'm not sure, possibly both. So, just a very brief run through. This is Rojas and Mediano's causal emergence. It needs a PID. Be careful. If you're going to use it, you have to say which PID. It uses unique information. And it says, essentially, this is the mereological interpretation. A macroscopic variable represents an emergent collective phenomenon insofar as it contains unique information about the microsystem as a whole, beyond information contained separately in parts of the microsystem, where part means a subset of microvariables of a certain size. So one thing to note is that the predictee variable, the target of prediction here, is the microsystem. This is T is the contemporaneous value. The macroscopic variable is the past, and you're conditioning on the past to them. So you're predicting the microscopic system, in fact. Now, and then just to say, they then show that for existence of these emergent variables, you need some kind of synergy in the system. I'm not going to go into that more detail on that. So this is our own dynamical independence. It's an informational closure principle. And what it says is that this quantity, which is the transfer entropy from the microscopic to the macroscopic, if that is equal to 0, then we describe that macroscopic variable as purely dynamically independent, so maximally emergent. And what it says is that there's no information transfer from micro to macro. Intuitively, the microscopic history does not enhance the degree to which your macroscopic variable already self-predicts. The macroscopic variable is informationally closed with respect to the microscopic system. So just to say, it's a quantitative thing. There's a measure of dynamical dependence. So that transfer entropy itself, we would call dynamical dependence. It measures the departure from emergence, if you like. In the same sense, this always seems to confuse people. I don't know why. It's the same as with, it's analogous to Shannon mutual information, which measures departure of 2 random variables from statistical independence. So you can think of dynamical independence as a kind of process dynamical version of statistical dependence. And scale in the DI sense means it's just a dimension of the macroscopic variable. So, one thing to note, which really struck me, is that in contrast to causal emergence, which we just saw, the prediction target here is now the macroscopic. So it's all about how well the microscopic predicts the macroscopic or not. And that's a very fundamental difference between these two superficially, in some ways, comparable emergence principles. And I find that quite striking, particularly as, Fernando Rosas was a colleague of mine. We tend to be very much on the same page when it comes to emergence and information theory in general. And yet we came up with these almost opposed versions of emergence. Not opposed, but they say very different things. So, right. So I'm going to speed this up a bit. So dynamical independence is not mereological at all. It doesn't even require the system to have parts, in fact. The best way to think of a dynamically independent of an emergent process, a macroscopic process, is that it's a kind of process in its own right, which is independent of its microscopic substrate. It predicts its own future kind of optimally. Knowing the microscopic past doesn't help you to predict the macroscopic system. That doesn't apply, it's kind of autonomous in the sense of that it self-predicts well. It may not. It can even be a white noise. In other words, not predict itself at all. Just mathematically, it turns out to be transitive, which means that, so I'll come back to that. Yes, sorry. It's transitive, meaning the upshot of that being that it accommodates hierarchical organization of macroscopic variables at different scales. It doesn't enforce, it doesn't require hierarchicality, but it accommodates it quite nicely. You can do some statistics with it. If you sort of cash this out in the Granger causality framework, you can do statistical inference because we know the statistical distribution of those variables. So small, or kind of nearly dynamically independent, could be interpreted in the statistical sense as the rejection of the null hypothesis that the vanishing dynamical dependence at some significance level. So what you can do then is you can say, look across all scales, look across all dimensions in your microscopic system, all possible scales, spatial scales, if you like. At any given scale, you can think of this landscape of all possible macroscopic variables at the scale. I can imagine that's a huge landscape. All the functions from microscopic to macroscopic at that scale. But if you look at the dynamical dependence at every point in that, in the set of all possible macroscopic variables, some of them will be more emergent than others. You get this kind of landscape on this space of macroscopic variables. Quite surprisingly, it may be actually well, not analytically, but computationally tractable to actually explore that space. And that we do. So, quick point: these macroscopic variables are not networks. Don't think of them as networks. Think of them more as kind of semi-autonomous subsystems of the microscopic system operating at a certain scale. Although you can say how much a network node participates in or contributes to the system. It's not a macroscopic variable, an emergent macroscopic variable in the sense, it's not a state of the system. It's not like the system is in the state of this macro variable. In fact, far from it. All these macro variables at all different scales will coexist. They're all happening at the same time. They can be dependent on each other, but they all exist. Sorry, this was the point of hierarchicalness. That point of that you can have all these dynamical emergent processes which coexist. How do they share information? Can they share information with each other? Do they communicate? What are their internal dynamics? Don't know, haven't been there yet, but certainly intend to. Finally, to notice that this can be done in the frequency domain, in the spectral domain as well, which in principle allows you to talk about emergence across temporal scales as well. And this is not all, An important point here is that, so the top two pictures are a couple of kind of, if you like, kind of poster children for emergence. So on the left we have flocking starlings, a murmuration of starlings. On the right we have a glider gun shooting out some gliders in Conway's Game of Life. Now, the point I'm trying to make here is that in both of those, you can pretty much see the macroscopic process. You can see that emergent. If you squint at that flock of starlings, so it just looks a bit blurry. You can see those kind of clouds or waves, and you can see that kind of process in its own right thing going on there. You can literally see it, as you can the glider gun. Now, the bottom picture, which unfortunately should have been an animated GIF, but I failed to get it to animate, is calcium imaging of a slice of mouse cortex, if I'm not mistaken. Now, if that were animated, what you would see there would just be like flickering neurons. You'd just see some flickering lights on a kind of dark background. That is the neural activity in a slice of mouse cortex. And you think, well, it seems quite plausible that there are some kind of emergent macroscopic processes which are underpinning all the cognitive phenomena in that mouse brain. It looks like nothing. It looks like noise. If there are emergent macroscopic processes there, you can't see them. You don't know what they are, unlike those other two cases. So our focus in looking at dynamical independence was very much on discovering these, can we automate the discovery of emergent macroscopic processes? I'm going to whiz through that here. Long story short is that yes, we can do it in using some linear state space modeling. There's quite a nice expression for that dynamical dependence in terms of the system parameters. L here represents the macroscopic process. You can take that thing and you can minimize it over the space of all macroscopic mappings, which in this kind of linear scenario turns out to be, if anyone's studied topology or Riemannian manifold theory, it's a well-known mathematical object called the Grassmannian manifold. That is the space of all, in this context, the space of all macroscopic variables. you can take this, you can minimize it over the Grassmannian manifolds and actually discover the maximally emergent processes, macroscopic processes, and you can do that at every scale. It's practical, it's something you can actually do. And you can do that in the spectral domain as well. So you could actually, what I'm saying here is that at least in this linear parametric scenario, yes, you need Gaussian assumptions, but there you go. It's a viable technique, something you can use, deploy in anger on real neurophysiological data. You can try and discover, you can try and map this emergence landscape. Just to say, okay, I've earlier mentioned these range causality maps. Maybe you can do this with some nonlinear systems like Langevin systems as well. There's some problems there, but I'm going to hurry this up. So then you can start asking, like, well, what can this dynamical independence, what can this flavor of emergence actually tell us about the multi-scale structure of brain dynamics? So very early days, but we already have this couple of papers by Boki Milinkovic, who's now working in Paris with Thomas and Rion. He's myself and Lionel, he's just completed his PhD a year ago, and he's now working as a postdoc in Paris. And he sort of really took these ideas and ran with them. And he did these two papers. And this one is still in preprint. It's in submission. I can't remember where now. This paper's out in PLOS Computational Biology. This is actually done in this kind of simulation in neural mass models. This is actually a study on EEG under anesthesia. And I'm going to have to whiz through this. But what both of these studies are looking at is essentially not actual macroscopic processes, but the landscape, this emergence landscape I was talking about. What Boki was trying to do there was to kind of map out this landscape and see what it can tell us, the neural correlates, if you like, of the emergence landscape and the dynamical brain state in these various states of consciousness. So the first one is just, it looks at emergent structure using minimal kind of biophysically plausible neural mass models. And the second study looks at emergence in wakeful rest and several anesthesia conditions. I hate slides with lots of talk, and I don't have time to go through these. Best you look at the papers. Just to say the results are really quite counterintuitive. They don't say what you might, they didn't say what we didn't find what we expected to find. That the structure of these emergence landscapes has a very different relationship than we'd expected. So I'm going to try and finish up very quickly there. So one thing you notice I haven't spoken about much, in fact, on that last slide, is consciousness. And those are just conscious kind of states rather than content or conscious, anything like that. So I'm going to finish up here just saying this nice little soundbite from Anil Seth. He says, the hard problem, I'm sure you'll know about that, the hard problem being, why is it like something to be conscious? What Anil says is the hard problem will not be solved, it will be dissolved. I had to ask him just before I left, did you actually ever say that? And he said, well, okay, I'm saying it now. The hard problem will not be solved, it will be dissolved. Anyway, the point he's making is that the history of science is the history of demagification. And that, you look in cosmology, you look in electromagnetism, the science of life, all these things were magical, they were mystical, and now they're not. And I think that the same will become true of consciousness science. We need these grand theories of consciousness. They're valid. Yeah? And I said, sorry, that's a bit cheeky, because being wrong is very instructive. Being wrong is better than being not even wrong. We established that. There's a whole bunch of big theories of consciousness. They can't all be right, but they will be instructively wrong, some of them. So other sensible advice, avoid secret sources. They tend to go out of flavor very quickly. Your elan vital, then luminiferous ether. Luminiferous luminiferous ether is great as an example of being wrong, because it was very influential in being very right about relativity, amongst other things. Try not to be not even wrong, because that's a waste of everybody's time, and use mathematical tools. This is how we do science. We theorize, we study the phenomenology, we gather evidence, we use that to validate our theory, and we keep on doing that. So the upshot is keep on doing what we're doing, and I'll end on that note. So thanks very much for listening. This is just a fraction of my colleagues in Cone